Okay, so thank you very much for the invitation to this workshop and this conference. And I'm going to talk about some work that I've done over the years with, so this is Michael Green, Eric Docker, Omer Gurdogan, and the last part about the single-valued correlation function is with Federico Zerbini, a mathematician, about where we actually discussed the property of the alpha prime expansion of closed strings amplitude. Martin ended up his talk with open problems, and he essentially talked about open string field theory. So this is a closed string talk, and actually since the question why there's only single-valued multiple zeta in the alpha prime expansion of any closed string amplitude is proven mathematically, as I will say, and physically, as I will explain. So this is as well a closed problem. But first I will start by giving some motivation behind this study. So, as you know, so this is the effective action of string theory that I'm writing here, for example. So this is a derivative expansion of the string effective action. So this is the Einstein-Hilbert term, this is the dilaton. And here this is the higher derivative expansion of the famous R to the fourth term. And we'll be essentially doing, this is for the type 2 superstring, where there's no R square terms. But the thing that is important is that in general, when you have, when you look at compactification of closed string theory to lower dimension, the coupling that you have in front of the higher derivative terms, they depend on the moduli, and they are very special type of functions. So these coefficients here are, as I will mention later, for the case of type 2b, they are modular form of when you are looking at type 2b in 10 dimension where the duality symmetry is SL2Z. But if you compactify down to lower dimensions, and if you keep maximal supersymmetry for type 2, then you have, of course, this function, a function of the moduli in the coset space, that is the duality group divided by the maximal compact subgroup, and they are invariant under the action of an element in the lattice that is given by the charge quantization. Okay, and so here I'm only writing the U1. Of course, you have terms that are. This is the bosonic term. You have terms that are with fermions with the same number of derivatives, so at each order and alpha prime, and this function. So here this is a function, but when you have something that carries a U1 charge, or that is, you have actually a form, and that can be transforming by some factor. So the thing that is important here is that this knowledge of this function is it's a non-perturbative, right? But so you can still nevertheless, is the string theory effective action. So these coefficients are constrained by unitarity, and this quantity contains both perturbative and non-perturbative contribution, and I will say a few words about that in a few slides. They are constrained by supersymmetry, and typically the way supersymmetry constrains this coefficient in the effective action is that it leads to differential equations that this coefficient satisfy. And of course, as I said, these functions are, because this is a lattice, this is a discrete subgroup, they are non-trivial functions constrained by the duality transformation. No, what I'm saying here is the superstring. So why is this important here? Is that this Okay, I see, this is a 10. So if I am in lower dimension, so this is a generic form for lower dimension. So think, for example, you are in 4 dimension. You have your higher derivative terms, and so this is a candidate counter term for a UV divergence of supergravity. But we are here in string theory. So this is a function, so this object is a function of the moduli, okay? Then if you try to go to the supergravity limit, you should find in that function the contribution to the UV divergence counter term. Okay? So of course there are issues about decoupling string states, as when you try to take the decoupling limit when you go from string theory to supergravity. But the point is that this function contains some coefficient times the log of, for example, the dilaton, the log of some scalar that is related to the dilaton in the dimension when you work, which actually is exactly given by as to match the UV divergence computation that you do in supergravity when this. So the point is that this is an extremely important data. So if you can construct all this automorphic form, you know everything about the UV behavior of maximal supergravity in various dimensions. So this is as well important if you want to construct some solutions. If you want to think about compactification of string theory or on some background, so you need to know all of these things. And you can as well test, actually, in the context of the ADS CFT correspondence, you can test the flat space limit of ADS correlator and the discontinuity of correlation function in N equal 4 and match it to some term that is contained in this function. So, in the case, for example, as I said, of the UV divergence in supergravity, the knowledge of this automorphic function exactly have been shown to match the counter term computed by Zwibern and his collaborator up to and including free loops. And when I'm saying including free loops, so that means it's the leading divergence up to free loop in the critical dimension, but as well the subleading. So when I am in a dimension, I have the R to the fourth is the counter term for the one loop divergence, but then there is some two loop divergence that is coming, and then this is contained as well. So everything matches. So everything wonderful. So of course the problem is that we haven't yet solved the finiteness of an equalate supergravity because determining this automorphic form is very complicated. Because for some reason I will mention later. But anyway. So if you want to have a good idea of the most up-to-date method and ideas about this automorphic program, I refer to this book that recently came out by Fly, Gustafsson, Kleinschmidt, and Persson, which explain all of this. But let me take a simpler case. So take type 2b in 10 dimensions. So there is the SL2R of the supergravity is broken to SL2Z. So the coefficients are functions that are invariant under the action of SL2Z. Okay, so this has to be invariant like that. And in that case, I am allowing a phase that has to do for the R symmetry charge. I think Michael Green may have given a talk about his recent paper with Kangwa about this anyway. So if I look at the R to the fourth term that is half BPS and the D to the fourth R to the fourth that is one quarter BPS, then you find that supersymmetry gives you that there is a very simple eigenvalue equation which is solved by this Eisenstein series. Okay? Simple. So let me look at what it is. So this Eisenstein says in the effective action of string theory, if I do a weak coupling expansion, so omega 2 is 1 over Gs. So if I normalize properly, I go from the Einstein frame to the string frame. I have, this is the tree-level term, zeta 3, and there is one loop, zeta 2, and non-perturbative. Then the D to the fourth R to the fourth, the quarter BPS, has a tree-level term, zeta 5, no one loop, and a zeta 4, two loop plus non-perturbative. Okay? The T to the 6 R to the fourth satisfies an equation that is inhomogeneous that is essentially, this is what you expect by having a on-shell deformation of the supersymmetry transformation that at this order in alpha prime kicks in the r to the fourth term that you had to put in the action. So it has some eigenvalue, and then the r to the fourth comes here. Okay, so this you know, you just have to solve this. So this object is not anymore an Eisenstein series, and you can write it using some advanced mathematics if you want. I mean, but for what is important here, you can extract the constant term here. So the constant term, so the zero Fourier mode, that means the zero charge sector when you look at the non-perturbative contribution. So this is the tree-level term, zeta 3 square. One loop, zeta 2, zeta 3. Two loop, zeta 4. Three loop, zeta 6. Plus, although if I want just to look at the zero charge sector, because there is the square of the Eisenstein series, here I have an exponential series. And so this term is something that is exponential minus omega 2. And because, and there is no charge. So this term already present in his expansion, some sector where there is no de Bruijn charge, but still a non-trivial exponential factor. And actually, this is a 1/8 BPS state, and actually, this is because you have instant on, anti-D instant on that contribute to that coupling. So this is the thing that come here. Okay, so this is just to tell you. So the thing that is interesting in what I said is that if you don't look forget for a while that there are exponentially suppressed terms, all the terms here that are coming from the perturbative expansion have some very, very distinct particular feature. So zeta 3, zeta 5, zeta 3 square. There's no zeta 2 at tree level. So at one loop, it's zeta 2 times 1, 0, zeta 2 times 0, zeta 2 times zeta 3. Actually, if you divide everything by zeta 2, you should get actually odd zeta values. Okay, so I'm not giving you too many examples so far, but I mean, and at genus 2, if you divide by zeta 4 as well, you should get something that is only involving odd zeta values. So the thing is that it may look a bit, so there's the question, so why is this? Because this is part of the, in this case that is SL2, if you know the constant term expansion, then by acting with SL2Z, you can get the function. Actually, this is the way the R to the fourth term was obtained, by just computing the tree level and then use the orbit under SL2Z. So there is the question, so what is the statement we can make about this coefficient that we have in the constant term expansion? So the thing is that the point is that this is exactly the point of the talk, is to explain what is special about this coefficient here, the tree level coefficient, and the one loop coefficient. So let me then state in a more generality the way I define closed string amplitude. So this is a generic closed string amplitude. So the 4-point amplitude corresponds in addition to n equal 1. That depends on polarization of your external states, whatever they want. They can be bosonic, fermions, whatever, your kinematical variables. And what I want to do is that I want to introduce here some building blocks times some coefficient of the kinematical variables. So the idea is that whatever string theory I have, if I'm computing an n-point function suppose I want to compute an n-graviton amplitude in bosonic string, or type 2 string, or heterotic string at tree level. What I want is that I'm introducing here some building blocks, that is here, such that if I know all these building blocks, whether or not I am in bosonic type 2 or heterotic string, I just have to tune what are the kinematic coefficients that are in front of it. So it's the same idea as having a basis of integrals when you compute integral in quantum field theory. If you have a basis of master integrals, this basis is the same for QED, QCD, or supergravity. So the only thing that depends are the kinematical coefficients. So, and the more symmetry the theory has, the more coefficient you are zero. So this is a finite sum at a given order in n. So generically, this object I define as, so the reason I have plus 3 is that I have fixed 3 points. So I have fixed 3 points as 0, 1, infinity. So I'm integrating over only the n points that are remaining. So this is the 4-point function I'm integrating over one puncture. And so I have here all the product of the difference between the position of my vertex operator between themselves to the power of the kinematical variable, so the alpha prime Sij, the 1 minus 0 and minus 1, okay? But what is important as well is that here I just have the variables to some integer powers. So wi to the ni, w bar ni bar, etc. 1 minus wi to mi, 1 minus w bar mi, etc. Okay? So these guys here are integer. They can be positive or negative, but they are integers. So this is why I don't have absolute values. So now, suppose if I take the 4-graviton amplitude, and which is the usual one that you are used to. There is the famous kinematical factor, and you know if you do this, if you do it in string theory and you take n equal 1, at some point you find an expression that is a sum of the odd zetas times the kinematic invariant. So that means if you expand this function in alpha prime, you find that there is the field theory pole, there is the zeta 3, the zeta 5, the zeta 3 squared that I've told you, and then zeta 7, zeta 3, zeta 3, zeta 5, etc. Okay? So now if you compare this expansion that comes by computing these integrals over the complex plane to an equivalent for gluon amplitude that you will compute in open string by having vertex operator on the boundary of a disk, you will see that you have so the field theory pole, the 1, and then the alpha prime square comes with zeta 2, the alpha prime cube zeta 3, the alpha prime 4 zeta 4, etc. So you see that here there's only odd zetas, and here there are even zetas as well. So these guys are powers of pi's, okay? So, excuse me? Oh yeah, I mean there are terms at all orders. I mean you just want to show that here there are zeta 2, zeta 4, that there is no zeta 2, zeta 4 here. There are zeta 3 as well. So there are everybody. Open string contains everybody. Closed string contains only that. So this is why I come. So this is, I think it's Stefan Stieberger, who the first time said that actually there is so the conjecture is that, and no, what I'm telling you in that talk is that this conjecture is proven, that actually in the closed string there is only a subset of zeta values that are called the single valued multiple zetas are introduced by Francis Braun. So let me tell you, so, and I think the first person to my knowledge that has formulated that was Stefan Stieberger, who said that closed string amplitude only involved the single valued multiple zeta of Francis Braun. So what are these multiple, yes? Yes. I mean, if I go to higher than, yes, because I just, so, well, you will understand. I mean, you will see. But I mean, so the point is that so here is the zeta values. Okay, so it's a multiple zeta. The multiple zeta is this ordered sum. You have integers and s. Okay, so depending on your convention, whether decreasing or so this is this. So this object is a number. This object is a function. So this is the multiple polylog depending on z. Okay, but if you take z equal 1, you clearly get that, right? So this is a number, this is a function. This function is a non-trivial function because it has branch cut. Okay? So it has, so this function has monodromy around z equals 0 and z equals 1, and this is the famous monodromy matrix of the polylog. So this is the monodromy matrix of the log, this is the monodromies of the d log, this is the monodromies of the Li3. So that means when you go around 0 and 1, then you pick phases, and then the discontinuity of the log is 2 pi, the discontinuity of Li2 is Li1, etc. Okay? So the thing is that you can introduce a single-valued version of this function. So, for example, Zagier had already in the past introduced a version of the polylog that is single-valued on the complex plane. Except, so you have to remove 2 points, 0 and 1. Okay, so it's like there's as well infinity, you remove 0, 1, infinity. But anyway, so the point is that, so you start with you see when k equal a minus 1, so this factor is not there. So this is Li to a minus 1, for example, Li3. If you, to Li3, you subtract the log of the modulus of z times Li2, and you take the real part, this function has no monodromies on the complex plane. It's single-valued. A simpler version, of course, is to take the log of 1 minus z, you take the real part of it, and then you get a single-valued function of the complex plane. Okay? No. There's no unique way. There's a choice in the way you kill the monodromies. Okay, but at the end, what's happened is that for the definition of the single-valued multiple zetas, is the same. I'm going to say it in a minute. Is the same space over Q, and it turns that what you get when you do the alpha prime expansion is there's a canonical definition given by Francis Braun, and it turns that string theory picks exactly the definition by Francis Braun. But anyway, so you can try to kill. There's no unique way to kill the monodromies, but whatever is not going to affect the following. So what's happening is that this function that has no monodromy, I call it SV, single-valued version. You can take its value at z equal 1. Okay. So what happens is that this function that has no monodromy at z equal 1, all the function that normally would, so all the Li2n of z, single-valued, at Li2n of z, single-valued, when you evaluate it at 1, gives 0. So that means the single-valued, this is the way you define the single-valued projection of any even zeta to be 0. The single-valued projection on an odd zeta obtained by the value at 1 of the single-valued, if you take z equal 1 here, you will see that actually for z equal 1 log z equals 0, you get Li3 of z, Li3 of 1, which is zeta 3, times the factor of 2. So that means all single-valued zeta 2n plus 1 is twice zeta 2n. So there's no unique way of removing, but actually Francis Braun introduced there's a canonical way that was introduced by Francis Braun. So now what happened is that the statement is the following: is that whatever way you define your single-valued multiple polylog, you get the same space of single-valued multiple zeta over Q. It's just linear combinations. You would maybe change, but anyway. So just to tell you how this thing simplifies, so at weight 11, this is all possible zeta, multiple zeta you can write. So there is zeta 11, but as well there is this irreducible zeta 3, 5, 3. And the statement is that all these guys are independent. You cannot find linear combinations with integer coefficient between these guys, or any of these guys. So the dimension is 11, and here are all zetas that contains a power of pi. So this is zeta 2, this is zeta 4 if you want, this is zeta 6, zeta 8, etc. So the single-valued projection of that space, you kill all the even zeta, so you remove the second line. The most surprising thing is that depth 2 multiple zeta. So this guy is an independent object as a multiple zeta value. But the single value projection actually is a product of single value. So it's not an independent object. So that means at weight 11, the basis of single valued multiple zeta is 3. With this guy being this. So the thing is that you could say, well, what is non-trivial is to have this depth 3 with this depth 2 guy together. So this one is in the basis. So you could say, since I am over Q, I could just, why don't I use just that guy as an element of my basis? It turns that actually this is the one that comes out from the canonical definition by Francis Braun. And it turns that it's exactly the guy that would come from string theory computation. Okay, so now the statement by actually Schlotterer, Stieberger, and Tom is that if you take the open string, you take your open string amplitude in alpha prime expansion, so you take the infinite series, you apply this single valued map, you should get exactly the closed string amplitude. Okay, so this fact has been proven. So this is a mathematical paper, the paper by Oliver Schlotterer and Oliver Schnetz came, I forgot, just after or just before? At the same time. Yeah. So he had given a talk about that, then they have their paper, then the paper came out, and we had been late. So anyway. And the method are different. So it's so what I want to show now is that first I want to show that what is the alpha prime expansion, alpha prime is here, of these building blocks of closed string amplitude. Okay, so the thing is that these building blocks of the closed string amplitude are numbers. Okay, so this is, we compute amplitude in string theory, don't compute correlation function. So what I want to do is that, in parallel to what I said about the definition of the single valued multiple zeta, I want to promote this. I want to see these building blocks of my string amplitude as values at z equal 1 of some correlation function. So what I do is that, the point is that when I'm discussing these building blocks, I don't have any more to, even if I want to study superstring theory, I don't care. I can construct my building block here in any theory, for example, bosonic string, or actually any CFT. So I will use the Coulomb gas. And then the only thing that I need is that the z equal 1 value is my physical building block. So I don't need that this is associated with any physical correlation function. The only thing I need is that this is a correlator function. This is a correlation function in a CFT. So that means because it's a correlation function in CFT, it has to be single valued respect to z. And so z is like as if you introduce a tachyon vertex operator here, which means that in the expression that you have here, you have z and z bar here. So in that expression, the powers, so I have here the modulus square with these GIJs are complex numbers. So this is why I need to have modulus square. But everybody that come with powers with no modulus have integer powers. So A, B, C's are integers. They can be positive and negative integers. I can have poles. And what is important is that as well, the difference between the left A's and A bars are integers. So the spin has to be integer. So I need that the difference between the left moving dimension here and the right moving for each of these guys, B minus B bar, C minus C bar, is an integer, which means I need to have integer spins. So because this is a correlation function, I can just decompose it on conformal blocks. So essentially, I'm splitting this integral over the complex plane in a product of two-ordered integral over the line. So I am having that is my closed string conformal block. My closed string correlator is this sum over conformal left moving and right moving conformal blocks with some coefficients. So by definition, these integrals are these ordered integrals over the line. So in that case, I have just the holomorphic part of the integrand, and I have to specify the way I'm integrating. So the order of the way I'm ordering the integration variables. So you have to think that it is as if you are on the boundary of a disk. So again, in the same way that this guy at value at z bar equal 1 is my closed string building blocks, the value at z equal 1 of this object will be our open string amplitude. So so this object that I've introduced here, actually, they are the so-called Amoto-Gelfand hypergeometric integrals, but because they are these open string conformal blocks, they are solution to the Knight-Zamolodchikov equation. By construction, I mean, it's easy to check that. And so they have the usual. So they are multi-valued. So these objects are multi-valued. Okay, these objects are multi-valued. This is multi-valued. This is multi-valued when z goes in the complex plane around 0 and 1. But this is single-valued. So all the thing is to make sure that the phases, the coefficient here, are such that you kill the monodromies. And this is again when I was insisting on the integer spin case, because you need that. If you don't have an integer spin, you cannot kill the monodromy from the left and the right, okay? So you just look at what is the monodromy of these integrals when z goes around 0, the monodromy of the integral when z goes around 1, so you have monodromy matrices z and 1, and the monodromy are compatible because you have, I mean, as I said many times already, in the integer spins. So the thing is that you may recognize this picture from some paper. Actually, I'm exactly using the paper by Dotsenko and Fateyev. So what they do for the Coulomb gas, I mean the 4-point correlation in Coulomb gas, is exactly what I'm doing. It's the same method. So so what happened is that the integral, the way I've defined them here, with this domain of integration where I have some variables between 0 and z and some variable between 1 and infinity, make that this integral have block diagonal monodromies around zeros. So these guys, this block here are a block of size factorial n, and this guy in the middle actually is a diagonal matrix of size n-1 factorial n. So no, what's happening is that these i's, they don't have diagonal monodromies around z equal 1. So I just need to do some change of variable and look at the monodromy around z equal 1. And then, so I have this function that I call j, that is just the I evaluated at 1 minus z. And now these guys have block diagonal monodromies around z equal 1. And the whole point is to just solve the system. To solve the system, so here I have a block diagonal monodromy on 0. Here I have the block diagonal monodromies around z equal 1, and to solve the system of linear equation, so that I have no monodromies anywhere in the complex plane. So the relation between, this relation between the j basis and the I basis is actually a linear relation. So the I integrals and these j integrals are related by a matrix equation. And this matrix equation actually is nothing else than if I take, if you take z equal 1, this is exactly doing the KLT, working out the KLT relations between the open string amplitude. So here z is not 1, but the point is that the matrix that goes in the middle doesn't depend on z. So this is what is called either the KLT matrix or as we called it, the momentum kernel matrix. So the compatibility between the two monodromies at 0 and 1, so I mean asking that this closed string correlation function has no monodromy means to solve a linear system, saying that the monodromy matrix around z equal 1 has to be the monodromy matrix around z equal 0 times this matrix of momentum kernel matrix changing basis. So the thing is that we find that the linear system has a unique solution up to a scale. So actually the proof is constructive and it works for any CFT models. So because what I'm doing, so the point is that, as I said at the beginning, I repeat it. So although I want to compute, for example, the alpha prime expansion in closed superstrings, once I have defined my building blocks, I can do it in any Coulomb gas free field theory. So the point is that everything that Dotsenko and Fadeyev did in their paper apply totally to what I said. So the thing is that it's already in their paper, although they cannot prove the solution exists, but mathematically, but physically, there are arguments for that. So the point is that you can prove that the linear system has a unique solution up to scale. You fix the ambiguity by matching to the physical amplitude, so then there is no more any ambiguities. So then what you find is that when you solve the system is that the element of the matrix, this matrix G and G hat, are rational function of sinus of pi alpha prime x, where x is a linear combination with integer coefficients of the kinematical variables. Then you need to know the alpha prime expansion of this function, this hypergeometric function, IR and JR. But this is actually known in the literature that there are just 2 pi i's and combination of multiple polylogarithm as function of z. So this object that is multi-valued has the multiple polylogarithm I discussed at the beginning of the talk. Their value at z equal 1 will give, as an alpha prime expansion, an object that has multiple zeta values and powers of 2 pi i's. The point is that because I put them together with this matrix J, then this my correlation function turns to have only single-valued multiple zeta. So this is the idea of the proof. So at z equal 1, what happens is that the J basis is the open string amplitude with this ordering of the external legs on the boundary of the disk. And there are a lot of this amplitude, lot of this integral that just vanish at z equal 1. So you find that my closed string building blocks is a KLT type. So the product of 2 open string amplitude times a matrix G hat. So, and this one has only, by construction, because I know it's the z equal 1 value of a function that has no monodromies, only single-valued multiple zetas. So actually, I'm not totally finished with the physical amplitude because, where is it? So what I have told you is that the alpha prime expansion of these building blocks has only single-valued multiple zetas. So now you have to do the expansion of the alpha prime because there's an alpha prime here in the kinematical coefficient to know the alpha prime expansion of that object. And it could be that this coefficient screws up everything. So for example, it could be that the kinematical coefficient contains log 2 or whatever. But of course, you know it doesn't. So the point is that so the kinematical coefficient are only rational functions of the kinematic invariant. Okay, so that means this guy never contains anything, any pi's, any 2's, any zetas, any logs 2. So that means it doesn't spoil the fact that I have only a single-valued multiple zetas in my expansion. But you know something. You know that, for example, because of the tachyon pole in heterotic string, you have 1 over 1 plus alpha prime s in front of the gamma function in the 4-point amplitude in heterotic strings. So because this guy can have a pole, then you can have you can have by expanding the alpha prime in alpha prime the kinematical coefficient time the building blocks here, you will mix various orders of the multiple zetas. So this object have a uniform weight for the multiple zetas at a given order in alpha prime. So if you look at some given order in alpha prime, the weight of the multiple zeta, the single value multiple zetas is correlated to the order in alpha prime. But in the amplitude, this is not true anymore because of the tachyonic pole you can have, for example, in chaotic string, where you can mix various order in alpha prime because of this. Anyway, so this is the way you prove, without having to compute anything, the fact that whatever any closed string theory. So although at the beginning of the talk I motivated my discussion by telling about type 2 superstring, this is true for, as I said, heterotic string, for example. So let me look at the 4-point case. So the 4-point case, the integral is this. Okay, so this is the building blocks that you have. And of course, as you know, depending on the type of correlator you have, dx, or psi, whatever. So these integers here can be 0, 1, -1, whatever. So the single-valued correlator, such that at value at 1 gives you that, is this, and with an appropriate relation between the c's, the b's, and the n's. So what you see here is that you see that, for example, when z equal 1, I have w minus 1 to the power b1 plus c1. That should correspond to 2 alpha prime k2 dot k3 plus, and I have to match it with the powers that I have here. So in a sense, I have some freedom in the way I'm splitting, the exponent when I'm introducing z. And this has to do with the freedom I mentioned earlier in making a single value definition of the multiple polylogs. So the way I'm introducing this correlator here, as you see, is not unique. But again, as the same logic as I was saying before with the single value multiple zetas, you don't care. What you care is that at the end, the result of your numbers, which is the closed string amplitude, the building block for the closed string amplitude, the space is the same modulo linear combinations. So if you do that for the 4-point case, you find that actually this correlator, you solve it, you find that actually the matrix, because it's just 2 by 2, zeros, and then here your rational function of the kinematic invariant. This object turned to be the open string amplitude. Actually, in the J basis, when you evaluate it at 1, this is 0, and this is just the open string. So you find that your closed string building block is the square of an open string amplitude with this kinematical coefficient. So we are using KLT formula to have just some sine function times no denominator and the product of two open string amplitude with different ordering. So actually it's totally equivalent to the standard KLT formula by using the relations between the various ordering between the open string amplitude. Then you can remove the denominator here, and then you have the usual. It's totally equivalent to the standard KLT formula. The thing that I find very interesting is that this monodromy consideration leads naturally to that non-local version of the KLT formula, if you want, which is actually something that we used when computing when we were computing this gravity amplitude. So suppose you want to compute the emission of two gravitons from a scalar, from a massive particle. So this is a massive particle with spin s and emits two gravitons. What you can do is that if you use you can do it whatever. So if you use in field theory, you want to write it using KLT in field theory. So you want to write it as a square or the product of two equivalent emission of two gluons from a massive particle in QCD, right? But the point is that, as we noticed, there's a channel where actually if this gravity amplitude, where gravity has normally the non-abelian graviton pole, which is the graviton self interaction, is actually a square of a QED amplitude. So this is the gravity amplitude, this one. This is a QED amplitude, where this is the emission of two photons from a massive charged particle, massive scalar, emitting two photons, and then a non-local kinematic coefficient. And it's exactly that formula. So the point is that the use Yes, yes. So if you call K, in that notation, if you call that K3, K4, it's K3, K4, K3, K4. So the point is that there is some interesting remark, the fact that if you play with the scale T formula, you can choose a channel when actually there is no non-abelian vertex here, because you can remove it by using, and because you don't change the color, everything is proportional to is in the U1 sector of the QCD computation. So your gravity amplitude is really a square of QED. And no. So X is your particle. It has a spin and mass. Okay, right? So this is the spin is here. Spin 0. So if you have a vector, massive vector, you take the quantum amplitude of a charged massive vector and emitting two photons, times the quantum amplitude of a massive scalar, the same mass for the scalar, emitting 2 photons. If you have a massive spin 1/2, but this is just QED. I mean, okay, we have you can just do it by doing the Feynman graphs if you want. But what I find amusing is that this is exactly the formula you get by looking at the single-valued thing. Okay, so now let me move to genus 1. So if you want to do the same as I did for the expansion of in alpha prime of not the genus 0 but genus 1 amplitude. So the genus 1 amplitude is an integral over the fundamental domain of a fundamental domain of SL2Z times the function of your kinematical invariant and tau, or the complex structure of your torus. So this B is the integral over the punctures of. So in that case, I'm looking at, because it's the one relevant for the R to the 4, for example, is the exponential of some linear combination alpha prime A psi j, my kinematical variables, times the Green function on your torus. So what you want to do is that you want to do an expansion in alpha prime. Okay, yes. So if you do an expansion in alpha prime, then I will integrate over the punctures. Okay. In that case, because it's genus 1, this is going to be a function of tau, right? So the expansion in alpha prime is it's higher order in alpha prime and the kinematic variables, and then it's a function of tau, and by construction, because nowhere I have broken the symmetry, the SL2 symmetries of my string perturbation, so I have that this is a modular invariant functions, or it could be as well a form, right? Okay, so if you are looking at quantities that involve some derivatives, so I could have something with derivative of the Green function as well, so you could have some charge. Okay, so but yeah, let's stay simple. I just have modular function. Okay. So and then at the end of the day, what you want is to get this zeta value, zeta 2 times zeta 3, zeta 2 times whatever that I mentioned at genus 1 at the beginning of the talk, is the result of integrating that object over the fundamental domain. Okay. So what I'm going to tell you is that this object again contains only single-valued zetas somewhere. So they are the modular generalization of the single-valued multiple zetas. So the Green function on the torus. So it's good to work with, anyway, this Green function, which is the Arakilov Green function. So it satisfies the usual differential equation. You make sure that you choose you integrate to 0 on the torus. And here you choose this one where there is no cube here, just 1. Of course, using the theta 1 over theta 1 prime, because the denominator doesn't depend on z, or choosing that one doesn't affect the amplitude, because by momentum conservation, this is totally innocent. But this one turns to have a better property because it's modular invariant by itself. The one with the eta cube, which comes from theta 1 prime at 0, is not. So this object here has this nice lattice representation in terms of Kronecker-Eisenstein series. So you see, here you see the propagator on the torus, and then you see the phase. Okay. But what is more important for me is that actually this object, I can write it this way. So let me show it like that. So I can write it as twice the real part of Li1. So Li1 is minus log of 1 minus z, so polylog 1. So of q to the n zeta plus sum of n bigger than 1 Li1 q to the n divided by zeta plus the constant term, the zero mode term, which is this Bernoulli polynomial, where q is 2i pi tau, zeta is 2i pi z, so this is z is the position of the puncture, so I'm going from a description of my elliptic curve that is multiplicative, c star divided by q to the z, and u and v, u is one of the Cartesian coordinates of my puncture on my torus. So the thing that is nice is that actually this is just the elliptic version of the D11, which is the single valued log that Zagier had introduced. And actually this modular form, the fact that you can write this object as this was actually done by Zagier in his paper a long time ago. So okay, so let me look at what you get. At some order in alpha prime, you will have to expand, you have to bring down from the exponential some powers of the propagators. Okay, so this is the one loop propagator. So let me look at the 4-point function. So I have 4 punctures of my torus. So I have n12 powers of g z1 minus z2. I have n23 powers of g2 minus g3, etc. So you can code the numbers at your, you can code the number of powers. You can code your graph by the matrix of the powers of the incident matrix of your graph. Okay, so the number of powers that you have for your propagators, and here the round on a line tells you that the powers. Okay, so this is this. So clearly that object is, if I integrate over z, it's only a function of tau. So what I can do is that because by using translation invariance, I can introduce a fictitious point on my torus, then make zeta as a variable. So this is a function on my torus. And when zeta equal 1, I'm back to that object. Okay? So at genus 0, this is the equivalent of the alpha prime expansion of your closed string amplitude. And so this is the equivalent of the building block, the alpha prime expansion of the building block I described at genus 0. So this is a function that now on this genus 1, actually by construction, everything is single valued here. This is single valued function, this is single valued. So this object has no branch cut in zeta. So by construction. So the thing is that I know that actually by doing the expansion, so this is because the powers are just powers, I mean this is polynomial, by doing the expansion, multiplying the polylog, nowhere I lose the fact that everything has no branch cut on the torus. I mean, so everywhere I'm keeping the fact that I'm single valued. So this object is really a single valued function of multiple elliptic generalization of multiple polylogs. So the value at 1 is the single valued generalization of the elliptic generalization of multiple zetas. So in concrete terms, for example, if I look at a graph where I have 2 dots and multiple propagators, which comes at in the alpha prime expansion, so this is this sum with this constraint. So we could show that actually this graph satisfies some nice differential equation where the inhomogeneous terms are the usual Eisenstein series and zeta values. And so you could check explicitly by the differential equation that it only contains single valued multiple zetas. And you can work out the expression of this function. You can compute the Q expansion of this object. And you see, well, rational terms, zeta 3, zeta 5, zeta 3 square, zeta 7. Okay. If you look at some other graph, like this one, triangle graph, you find at weight 7 a graph that contains all of these ones, okay, and this weight 11. So here it's a modular function that is a non-trivial modular form that has in its Q expansion a non-trivial single-valued multiple zetas. So I am at weight 11, and I have all the guys that I told you are in the basis. So the point is that this at weight 13 as well, there are some non-trivial multiple zetas, but because this is the highest term in the 1/2 expansion here, there's only a single, we don't see the other guys. So the point is that the conjecture now is that actually when you compute the closed string amplitude, like that, okay? If you do the expansion in alpha prime, you do the integration over your punctures, you will generate here modular function. The constant term of this object contains all the single-valued multiple zetas, so it covers everything. So at tree level, at genus 0, that was just numbers that were not modular functions, but it was proven that actually we cover all the space. Here, it's a conjecture whether or not we cover all the space, but I think it would be surprising if string theory misses something, okay? And I'm going to finish on that. So, which is that, what we are seeing is that actually by using, we can, at genus 0 and genus 1, show that the alpha prime expansion of any amplitude. So what I said is completely independent of the type of matter of the external vertex operators. In closed string, any closed string theory only involves this special number that is called the single-valued multiple zetas. It's important because the space of the single-valued multiple zetas is much smaller. So if you want to think in terms of injecting this result in the effective action and then using it to connect this with some result in quantum field theory, that gives some very strong constraints on what string theory predicts as possible correction to your effective action, particularly so the quantum term of the UV divergence or whatever. So the thing is that the construction is actually very simple, is that you use the fact that you construct some correlator in CFTs that you know are single valued by construction. And so at genus 0 and genus 1 you can do it explicitly, but nothing prevents me to construct some correlator at any genus order. Okay, so it's you can my only limitation to not go to genus 2 amplitude in string theory is that I have troubles I mean beyond the 4-point amplitude to do anything higher genus. But the point is that the fact that actually the string amplitude that are numbers that can come from a specialization of some single valued correlator. I mean, the single valued correlator, because it doesn't have to come from physical amplitude. This is some formal construction, can be done to any order. So in a sense, the idea gives confidence to the fact that the closed string amplitude has only the single valued zetas in its expansion. So it would be good to see how this can be used to higher order in perturbation, and in particular in connection with the recent work by Boris Piolin, Michael Green, and Eric Docker on what they did about the low energy expansion of the 4-graviton amplitude at genus 2. So thank you. Okay, so first, I'm going to answer your question, but so first I didn't use a single valued projection. What I did is that I constructed a function. So I never had to refer to the open string. Okay, so I constructed. I stayed within closed string theory. I constructed single valued object that when I evaluate it to 1 gives me the closed string amplitude. So I never have to make a reference to the open string explicitly. Although, of course, they come because I use the conformal block the decomposition and the open string are the multi-valued conformal blocks. But so I don't. So the point is that what is confusing is that indeed normally you think about the open string arising by the involution from the closed string, right? And the point is, so you have the closed string amplitude. You have your involution, you can construct the open string. So you construct the green function and you can construct the various D annulus. So the single valued goes backward, okay? So the single valued takes the object and in a sense does the opposite of what does the involution coming from the closed string to the open string, okay? I would like to see exactly how this thing goes, okay? So, of course, on the sphere, everything is trivial because on the sphere, the closed string the closed string Green's function is this, okay? And the open string is this. Oh, okay. Let me say like that, okay? So this is the whole difference between having Zi minus Zj to the 2 alpha prime S and Z to the 2 alpha to the alpha prime S, okay? Because here I have an absolute value, so I don't have to care about where these points are positioned with respect to each others. Here, of course, you have to take a determination of the log, right? So what's happening is that the single valued projection is actually taking the real part of that guy. So this is the SV construction of the polylog. So this is on GNU 0. So on GNU 0, you go from this object that is multi-valued, you take the real part, you get single valued, right? And the involution, so making the sphere, whatever, the disk, goes this way. So the point is that at genus 1, there should be a way to understand as well how this goes, because we know how to construct everything explicitly downstairs from the closed string correlation function, from the closed string Green's function, right? But this has not been done, right? So it's and the way the single value map is used by Oliver, for example, doesn't make very apparent the connection with the involutions. So it's, you can say maybe it's the inverse, but there's some ambiguity somewhere. So the point is that what should be interesting to ask is that why is when you do the alpha prime expansion of string theory, you land exactly on the definition that Francis Brown gave, because he had to make some choice of a base point when he computes the single valued multiple polylog, and it turns that actually